Hello, welcome to this video. Today we're going to do this problem. This is going to be a functional equation, but sort of a different kind. So we need to find all functions f from the natural numbers to the real numbers that satisfy f of v plus e plus f of f equals 2f of e plus 1. Now I need to explain what v, e, and f symbolize. So this functional equation is for all simple planar connected graphs, where v is the number of vertices in that graph, e is its number of edges, and v is its number of faces. So first of all, I need to explain what is a graph, what is a simple graph, a planar graph, a connected graph, and talk about a little bit about the relations of v, e, and f in those sorts of graphs. So graph in math is just is points. It could be in a plane, could be in a 3D space with edges between them. So say so this is a graph. The edges don't have to be straight. This also classifies as an edge. Just needs to be points with lines, not necessarily straight lines between them. And that's a graph. Could be in a plane, could be in a 3D space, could be in any environment you want. A simple graph is a graph where any two points in the graph have at most one edge connecting between them. So and no edge connects a point to itself. So if this is a point, this technically is a graph, an edge of a point to itself, an edge from one point to itself, but this is not allowed because this is not simple. Another example is, say we have 2 points, we have one edge. Now it is still a simple graph, but now this is no longer a simple graph since we have 2 edges connecting between two points, and we only can have at most one. So this is also not simple. And of course, any graph that includes any one of these is also not simple. But so we're only looking at simple graphs. So this, for example, is a simple graph. Any 2 points here have at most one edge connecting straight between them. A planar graph is a graph that you can put on a plane, like this one, where no 2 edges intersect. So for example, a graph like, so far this is a normal, this is a planar graph, everything's alright. Here, this is where there's a problem. This is not a vertice. This is just where 2 edges intersect. This is not a planar graph since we put it on a plane and 2 edges intersect. But it is, however, simple since any 2 points do have still one edge connecting straight between them. However, you can sort of modify this graph. So this is not planar, but you can sort of modify this graph to make it planar. Instead of, let's say you want to make an edge between these 2 points. Instead of making here, you can make it around. So this is another edge, and now this is a planar graph. But there are also examples of graphs where, I'm sure we can make one yourself, but there's also examples of graphs where no matter how you rearrange these edges, you can never put it on a plane such that no 2 intersect. But the first one we had, with the original one we had where we had an edge here, it also wasn't planar. Now let's talk about what a connected graph is. Connected graph is a graph where there is a path of edges that leads from any one point to any other point. So let's do an example. Here, this graph is connected, since I can get from any point to any point. So from say this point to this point, I can walk on this edge, then on this edge. From this point to this point, I can go on this one, then on this one, then on this one. An example of a not connected graph is maybe this thing. So it is simple and it is planar, but it is not connected, since these 2 points, for example, don't have a path connecting between them. Right there. If I start here, then anywhere I go, I'll still stay on this triangle, and I'll never be able to make it to this place to get to this point. So these are also not allowed. And this is an example of a graph we can use. It is simple because any 2 points have at most one edge connecting between them. It is planar, since this is because we put it on a plane and no 2 edges intersect, of course except the vertices. And it is connected, since I can get from any point to any other point. So these are sorts of graphs we're looking at. And now, after we explain that, let's actually solve this equation. So now let's maybe continue to further explain what V, E, and F are. So V is the number of vertices. It's very straightforward. So in this example, we have 5 vertices. We have 1, 2, 3, 4, 5. So in this example, V is equal to 5. The amount of edges is also 5. That's just by chance. They don't have to be the same, obviously. So we have this edge, this edge, this edge, this edge, and this edge. So E is also equal to 5. And F, you might be thinking, okay, we have one face here, like this face here, and so F would be 1. But that's incorrect. In graphs, when we count faces, we count those like on the inside, on the ones that are like bounded by edges, and the one on the outside. So on the outside, you can think of as like the rest of the plane is also a face. So anything like on the outside of this plane is also a face. So in this case, F is equal to 2. So we have this one bounded by these edges, and the one that's like the rest of the plane. So that's just an example of what V, E, and F mean on a graph. Now, let's see. So now, this is what the functional equation is telling us. Take any simple planar connected graph, like this one, and let V be its number of vertices, E its number of edges, and F its number of faces. So in this case, we'd have 5, 5, 2. Find all the functions that for any simple planar connected graph, we will have F of V plus E plus F of F is 2F of E plus 1. So in this case, we would have F of 10 plus F of 2 is 2F of 6. So let's begin. So the way to do that, or at least the way I thought of initially to do this, is to find graphs with like general graphs with n vertices that are simple enough that we can actually say what V, E, and F are, and put them into this functional equation and get things about F until we just have a couple of algebraic equations that we can use to get what F is. So the first graph we're going to draw is very simple. It's going to be this sort of graph. So here specifically I have 7 points, but generally I'm gonna take n points. So just n points in a circle. So here we have, we defined n vertices. The amount of edges is also n. And number of faces is 2. right? I have this on the inside and the one on the outside. So from this we get f of 2n plus f of 2 equals 2f of n plus 1. Now we also need to keep in mind what range n has to be in. Since if we try to do this for, say, 2 points, we wouldn't be able to do it. We'd end up with something like this. It doesn't work here. In this example, v is equal to 2, but e is equal to 1 and f is 1. Meaning that n has to be bigger than or equal to 3. Since in that point you can draw a triangle, and then a square, and then a pentagon, hexagon, and so on and so forth. And now we're going to do something similar. I'm going to take the same thing, but draw 2 edges. So for this one, I'm going to draw one edge and another edge. So now n has to be bigger than or equal to 5. Since I can't do that in a triangle, I can't draw any more segments here. And in something like a square or a rectangle or anything like that, in any quadrilateral, I can't do that, but I can only draw one triangle, and the other triangle already intersects it. And if I draw it around, it's gonna add like a face here that's like we sort of not counting here. It's a bit weird. So we're just not gonna look at that case. But from n is equal to 5 onwards, if I have, say, a pentagon, I can draw 2 different diagonals, and everything works. After that, a hexagon, then a hexagon, a 7gon, and so on. So in this case, let's see. The number of vertices is still n. So now v is still n. E was n, but we added 2 diagonals, so now it's n plus 2. And f is equal to, well, let's count. 1, 2, 3, and the one on the outside, 4. So f would be 4. And from this we get the equation f of 2n plus 2 plus f of 4 is equal to 2f of n plus 3. Okay, we can work with these. Now if we substitute n plus 1 into this equation, we get f of 2n plus 2 plus f of 2 is equal to 2f of n plus 2. So now we can subtract these equations and divide by 2 to get f of n plus 3 minus f of n plus 2 is equal to f of 4 minus f of 2 over 2. So this applies for n bigger than or equal to 5. So, but if I replace here n with n minus 2, I'll get that this applies for n bigger than or equal to 7. So f of n plus 1 minus f of n is some constant, I'll call it a. And this applies for n bigger than or equal to 7. But now, this is just an arithmetic sequence. So a number minus the number previous to that number is equal to just a constant. So that's just an arithmetic sequence, meaning that we found that for n bigger than or equal to 7, f of n is some a times n plus b. Okay? But now we still need to take care of 1, 2, 3, 4, 5, and 6. Well, of 2 and 4 we can already take care of here. Because if we take n to be big enough here, say n is equal to 10, doesn't matter, the n will cancel out. But if we take a big enough n, you can calculate and see that we'll get, after subtracting this from this side, that f of 2 is equal to 2a plus b. And similarly, if I plug in n, that is bigger than or equal to 4 here, so both of these are bigger than or equal to 7, I'll end up with f of 4 being 4a plus b. So now we took care of 2 and 4, we take care of 1, 3, 5, and 6. Okay, so far we found out that f of n is linear, or 8 times n plus b, for n that is bigger than or equal to 7, and n is equal to 2 and n is equal to 4. Now we need to take care of 1, 3, 5, and 6. And we're going to do that with another equation. We're going to come up with another graph. So the graph we're going to take is the following one. Let's take n points, and let's take n plus 1 points, and let's draw all the edges from n points to 1 point. So in this case, we'll have like n is equal to 5, since we have 6 points, and we have 5 edges, and this time f is equal to 1. So the number of faces is equal to 1, since like there aren't 3 edges that like are bounding on triangle or a quadrilateral or whatever. We just have the entire plane as one face. So in this case, v is equal to n plus 1, e is equal to n, and f is equal to 1. And here, this time, n is just any natural number. Since we can do this with just n is equal to 1, it's going to be this thing. And for n is equal to 2, it's going to look like this, and so on and so forth. So this we can do for any natural number n. And when we plug it into here, we get f of 2n plus 1 plus f of 1 is equal to 2 times f of n plus 1. So this is what we're going to use, and this is just going to be for all n. And this is what we're going to use to take care of 1, 3, 5, and 6. So first of all, if I take an n that is bigger than or equal to 6, these two, 2n plus 1 and n plus 1, are bigger than or equal to 7. And then, so I'll be able to just use this a times n plus b. So I'll get 2an plus a, so this is this times a, plus b, plus f of 1 is equal to 2 times an plus a plus b, which is 2an plus 2a plus 2b. So 2an goes with 2an, a and 2a makes this 1a, and b with 2b makes this 1b. So now we got f of 1 is equal to a plus b, which is a times 1 plus b. So we also took care of n equal to 1. Now we need to take care of 3, 5, and 6. To take care of 3, we can plug into here n is equal to 1, and we get f of 3 is equal to 2 times f of 2 minus f of 1. We know what f of 2 is, it's 2a plus b, and f of 1 is a plus b. So we get that 2f of 2 minus f of 1, with a little bit of algebra, is 3a plus b. And so, after plugging in it, plugging in n is equal to 1, it gives us f of 3 equals 3a plus b. Now we need to take care of 5 and 6. And if we plug into here n is equal to 2, we get that f of 5 plus f of 1 is 2f of 3. So f of 5 is equal to 2f of 3 minus f of 1. We know what f of 3 is, and we know what f of 1 is. So again, a little bit of algebra. After plugging in n is equal to 3, we get that f of 5 is equal to 5a plus b. We just need to take care of 6. And to take care of 6, I'm going to plug in n is equal to 5. So this is going to be f of 11 plus f of 1 all over 2 is equal to f of 6. We know what f of 11 is. It's 11a plus b. Plus f of 1, which is a plus b, we'll get 12a plus 2b. Divided by 2 is 6a plus b. So plugging in n is equal to 5 gives us that f of 6 is equal to 6a plus b. So this part of the problem was really just checking these, like sort of checking small cases and showing they're also linear. But look at what we got. We got that f of 1 follows this a times 1 plus b. F of 2 we proved earlier, 2 times a plus b. 3 times a plus b, we proved earlier, 4 times a plus b. 5 times a plus b, and 6 times a plus b. And earlier we also proved, and for n bigger than or equal to 7, this is f of n is a n plus b. Meaning that all in all, we got that f of n is equal to a times n plus b for all natural numbers n. So we just found the function f, but now we need to check that this function actually satisfies this. So let's do this here. So let's plug it in. We'll have AV plus AE plus B plus AF plus B is equal to 2 times AE plus A plus B. So here we'll have 2B, and here we'll have 2B, so that cancels out. And we get, here we have AE, here we have 2AE, so we can erase this and put here a minus sign. And we get, if we move the 2A also to the other side, we'll end up with A times V minus E plus F minus 2 is equal to 0. And this is equivalent to the original equation. Since we didn't divide by anything, we just moved things around. So now, is this always equal to 0? The answer is yes. Because any graph that is simple and planar and connected, well, it doesn't have to be simple. Any planar connected graph satisfies this Euler's formula, one of his famous equations. V minus E plus F is equal to 2. So V minus E plus F minus 2 is always equal to 0 for any planar connected graph. This is true. So also namely in our case for any simple planar connected graph, meaning that this is always 0. Meaning that for any linear function f, this functional equation holds, and we've shown that f has to be linear, so the final answer is that f can be any linear function. So, and a and b can be real numbers, don't have to be natural numbers, since f is from the naturals to the reals. So something like 2a, so f of n can be like 2n minus 1, or square root 2n plus 5, anything. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.